So we're going to go ahead and take a look at the integrated rate laws and how they expand our ability to analyze the kinetics of reactions. So why would we utilize integrated rate laws? Well, differential rate laws, or the rate laws that we've already been utilizing, only allow us to relate or express rate as a function of reactant concentration. Okay, so we've been utilizing, rate laws that look something like this. And basically, the rate is proportional to some order of the concentration of your reactant. Now, the integrated rate laws basically allow us to relate the concentration of a reactant as a function of time. Okay, so basically, it allows us to basically expand upon a way that we can actually analyze the kinetics of a specific reaction. Okay, and these can be first order, second order, or 0th order. And basically, the way that we obtain the integrated rate laws is we perform calculus operations on them. So basically, we integrate the rate laws, the differential rate laws, and subsequently get these integrated rate laws. Now, you will not be expected to know how to do the calculus behind it. You will just be able to use the equations and approach it from that type of perspective. Okay, so if we look at this reaction here, we could take our rate law that we would figure out experimentally, our differential rate law, and basically understand that obviously this is first order. Our n value is equal to 1. Okay, and we know in that situation that if we double our concentration, then we double our rate of our reaction because it is first order. Now, if we integrate it and get our integrated rate law, this is what a first order integrated rate law would look like for this specific reaction. Okay, so what I want you to notice is the generic setup is that you are plugging in basically a concentration at any specific time, and that's going to be equal to your rate constant times time plus the natural log of the reactant that you're looking at your initial time, so before the reaction has started. So this relationship, okay, subsequently now obviously includes a time component in terms of our analysis of our concentration, and of course the time component with respect to the overall rate of reaction. Okay, so remember guys, the not symbol that you see down here, that indicates the concentration of that substance at the initial start of the reaction. Okay, and the sub T indicates that this can be at various times within the reaction progression. So for first order integrated rate laws, we can actually use them to find quite a bit of information out. So remember, your integrated first order rate law looks like the following. And basically we have a whole lot more variables in this type of equation. And so we can utilize this equation to find the concentration of a reactant at any time after the reaction has started. And we know this obviously because we have a concentration variable at the initial time. We have a time variable, okay, and if we know our initial concentration and the time at which we're trying to basically analyze, 10 seconds into the reaction or 5 minutes into the reaction, we can plug that information in and subsequently obtain our concentration at that specific time slot. Okay. We can also figure out the time interval required for a given fraction of sample to react. Okay, so basically we can look at the relationship between our initial concentration and our concentration at a specific time. Okay, and we can look at the ratio that will form there, and that can subsequently lead us to basically the time value in which that concentration ratio will occur. And the time interval required for a reactant concentration to fall to a certain level. If I know my initial concentration and I say, hey, I think this is the specific concentration that I want pay attention to. I can plug those values in and subsequently solve for my time variable. Okay, so with respect to first order reactions, obviously it's very helpful with being able to find specific information out at specific times throughout the reaction progression. Okay, let's go ahead and let's look at a little bit more detail of the first order integrated rate laws. Okay, so once again we have our generic form of the integrated first order rate laws. Okay, remember we have our concentration of the natural log of our concentration of our reactant at a specific time. We have our rate constant, we have our time value, okay, and we have the natural log of our initial concentration of reactant. Okay, so this relationship basically should bring several things to our mind. Basically, you know, the concentration of A is going to be dependent on time, right? So basically the relationship that you see here, there's a direct relationship between our time and our subsequent concentration values. As the reaction progresses, you're obviously going to see a change in your concentration. Okay, if we look at this generic first order integrated rate law and we look at it with respect to the y equals mx plus b equation, we can glean some information about the reaction type from graphing the natural log of our concentration of our substance versus time. Okay, so if we take the natural log of a specific substance versus time, we can plug that in, okay, we should get a straight line. Okay, so basically our slope is going to be equal to our rate constant, and our slope should be negative with respect to this type of equation. Okay, this rate law can also be expressed as a ratio. Basically, we move our natural log on over, okay, and so we can relate our time and rate constant to the relationship between our concentration initial and our concentration of our reactant as the reaction progresses. Okay, so basically the integrated rate law for first order reactions is very useful. If we want to know if we have a first order reaction, we can graph the natural log of our concentrations versus time, and if we get a straight line with that negative slope, basically we know that we have a first order reaction. Okay, so there's definitely information we can glean from the graphical analysis of these reactions or these integrated rate laws, and that can help lead us to different information that will subsequently be helpful. Okay, so the integrated rate laws can also be utilized to allow us to find our rate constant K, okay, that we see here. So if we're just utilizing our N2O5 decomposition example that we've been using over and over, we know that that's a first order reaction, okay, and so we know that the integrated rate law for this specific reaction will look like this. Okay, make sure I add in that sub T. Okay, and basically if we want to figure out our rate constant for this specific reaction, we can take the data that we have, plug in a few pieces of it, and subsequently figure out the rate constant from that perspective. Okay, so what are we going to do here? All right, what we're going to do is we are going to find our concentration initial, okay, and we're going to plug that in. Okay, so concentration at time 0. Okay, we're going to find the concentration at the time in which we want to look. So in this case, we're actually going to go all the way to the 400 second mark. We're going to use the entire row, basically. Okay, and we're going to plug in the concentration at that time. Okay, and basically take the natural log of this ratio here. Okay, and then we're going to divide it out by the time that has passed, okay, for that progression to occur. So basically from 0 to 400 seconds, so 400 seconds is how long it's taken for it to occur. So basically our rate constant for k is going to be as follows. Make sure you're also paying attention to the negative signs and how they cancel each other out in this process. So let's go ahead and let's look at second order reaction. Okay, so we know that the differential rate laws for second order reactions look like such. Okay, obviously we can also have multiple reactants, both with first order setups. So to give us an overall second order overall reaction. However, we're going to keep it simple. So basically, when we do the integration, when we take the integral of the differential rate law, we subsequently get this equation. Okay, so similar concept or setup as we saw with the first order, except in this case, obviously, we're dealing with a slightly different answer. Okay, so just like first order reactions, the concentration of your reaction is going to depend on the time progression. Okay, so as time progresses, the concentration will change. Okay, now if I want to check and see if a reaction is in fact second order, okay, I'll take a plot of 1 over the concentration of my reactant versus time. And if I get a straight line with a positive K value, that's going to be indicative of a second order reaction. Okay, so basically much in the same way that we could utilize the first order reactions to find out different information about K or even a specific concentration at a specific time. We can do all these same things, it's just in this case we're going to be using a slightly different equation. So zero order rate laws are basically kind of rare. Most reactions are not going to have a zero order rate law. And the zero order rate law, the differential, looks like this. And as you can see, when we convert this into the integrated rate law, we get this equation here. Okay. And basically something to know about this is that this is the type of kinetics seen when enzymes are present. It's very common there. So things to note about zero order rate laws, basically it doesn't depend on concentration. Okay, so what do I mean by that? Well, the rate of your reaction for, say, a first order reaction, as you can see, as the concentration changes, the rate of your reaction is also going to change, right? Okay, so as time progresses, this line kind of flattens out because the rate of the reaction is actually dependent on the concentration of your reactants. Okay, in the case of zero order zero order reactions, okay, the concentration doesn't affect the rate. Okay, so if you plot a concentration of reactant versus time plot, and you basically get a straight line with a negative slope, you subsequently know that you have a zero order rate law. So none of these equations are going to be provided for you. It's going to be assumed that you know what they are, and for each of the three types, the first, second, and zero order rate laws, you guys need to be able to differentiate between the integrated rate law and the differential rate laws. Okay, so when you're asked for them, please make sure that you write the appropriate equation. Okay, so make sure that you guys are spending a little time memorizing them. Also, please consider and spend some time with the graphs. Okay, we want to be looking at, what are we graphing versus time, okay, in order to get our specific slope. What kind of slope do we need, and what does it tell us about that specific reaction? So, your zeroth order is going to have, this straight line with a negative slope. Okay, your second order rate laws, when you graph 1 over your concentration versus time, okay, you're going to expect that positive slope. Okay, and when you graph the natural log of your concentration versus time, okay, you should also get a negative slope, sloping line for your first order reaction. So make sure that you're spending time with those, organize them in a way in which you can kind of visualize what the graphs look like with the integrated rate law and what the differential rate laws will look like.